Hi folks, today we're going to look at what are called hyperbolic functions. And hyperbolic functions, the two main ones, are the two most basic ones, are cos x and sine x. Cos x and sine x. And they look quite like trigonometric functions, don't they? But they're also act quite like them as well. If you remember that cos x, we can write in terms of an exponential, half e to the ix plus e to the minus ix. And sine x we're able to write as 1 over 2i e to the ix minus e to the minus ix. So we're able to write sine and cos in terms of exponentials. And it's the same for cos x and sine x, but they're even easier, to be honest. Cos x is a half of e to the x plus e to the minus x, and sine x is a half of e to the x minus e to the minus x. So if we're using those definitions, we need to know those inside out. But we could use those then to evaluate values of cos x and sine x. So for example, we want to use cos 2. Then what we could do is we could write down the exponential derivative of cos x, which is a half e to the x plus e to the minus x. And instead of x, we put in 2, so that's a half e squared plus e to the minus 2. And we could work out these two values on our calculator and just fill it in. Or something a bit trickier, sine of log 2, and we'll see quite a few questions like this, sine of log 2, if we're asked to evaluate that well. Sine x is equal to half e to the x minus e to the minus x. So the sine of log 2 is equal to a half of e to the log 2 minus e to the minus log 2. Well, e to the log 2 is just 2. And e to the minus log 2, well that's if we look over here, that's 1 over e to the log 2. And e to the log 2 is just 2. The exponential and the log function cancel each other out. They're inverses of one another. And so we're just left with a 2. And so we've got 2 minus a half here. And then we multiply it by half, so we get 3/4. So we can use these definitions of cos x and sine x to evaluate things like this. Also then in trigonometry, we end up with tan x, and we know that tan x is sine over cos. And we have a very, very similar one for hyperbolic functions as well. And that is tanh x. Tanh x, so it's tan with an h on the end and then x. And again, we can see that tanh x is sine x over cos x. And when we put these values, the exponential derivatives in, they cancel down to this here, e to the 2x minus 1 over e to the 2x plus 1. If you write sine x as a half of e to the x minus 1 over e to the x, and then get a common denominator, then you see that sine x is a half of e to the 2x minus 1 over ex. And similarly for cos x, you get that. And when we divide one by the other, this is what we get for tanh x. So it's very, very similar to what we have in trigonometry. And likewise, in trigonometry, we need to know the graphs of sine, cos, and tan. It's the same for sine, cos, and tan. The graph of y equals sine x is this one here. And you'll notice that if you rotated this graph through 180 degrees about the origin, it would be exactly the same. And so that means that the graph of y equals sine x is an odd function. The graph of y equals cos x then is this curve, almost quadratic looking, and it goes through the point 0, 1. And it's symmetric about the y-axis, which makes this an even function. It's also what we call a catenary. The hyperbolic cosine or cos x is what sometimes engineers use to model, say, a wire that's hanging or a chain that's hanging between 2 points. So this is something that's used in real life. And I guess hyperbolic functions in general, they're not fairly widely used, but something like that then can come up in engineering quite a lot, or building. You'll find that hyperbolic functions are useful for electronics, for developing circuits, and electrical engineering as well. So they are used, even if it's not particularly common. And finally, the graph of tangent x looks like this. We have two asymptotes at 1 and minus 1. Excuse me. And tangent x looks like so. It goes through the point 0, 0. But like in trigonometry, we have 1 over sine is equal to cosec. 1 over cos is secant, and 1 over tan is cotangent. We have the same in hyperbolic functions as well. So sec is same as 1 over cos x. And so if we look back to our values here for cos x, it's e to the 2x plus 1 over 2e to the x. When we turn that upside down, there's what we get. Same for cosec x, that's 1 over sine x. Cosec x would be 1 over sine x, so cosec x is 1 over sine x, and we just flip that upside down. And coth x is 1 over tangent x, and again, we can just reverse the numerator and denominator. In terms of their graphs, you can see that the graph of sine x goes through 0. So at 0 we have asymptotes for 1 over sine x or cosec x. You see for cos x, it goes through the point 1, 0. And so 1 over cos x also goes through the point 1, 0. And as this x tends to infinity, cos x tends to infinity as well. So you find that 1 over that, as x tends to infinity, it tends to 1 over infinity, tends to 0. And the graph of coth x then has asymptotes still at 1 and minus 1, and an asymptote of the x-axis as well. So that's basically your hyperbolic functions. And we need to know how to use those definitions. So, for example, if I have a cosh of log 5 and I'm asked to do this without a calculator, which you may well be asked to do, I know that cosh is a half of e to the power of whatever this is, so it's log 5, plus e to the power of minus x, or in this case, minus log 5. So that's a half upon, well, I know e to the log 5 is just 5. This is 1 over e to the log 5. So this is a half of 5 plus 1/5, which is a half upon, what's that, 26 over 5, which is, 13 over 5, 13/5. And so we can evaluate that quite quickly. A slightly harder one over here, but we're going to do it in the same sort of fashion. I know that the cosh of x is equal to a half of e to the power of, whatever this might be, plus e to the power of minus, whatever this might be. Now, because this is a log function, I'm going to write this, instead of 2 log of 1 plus root 2, I'm just going to write it as the log of 1 plus root 2 all squared. That's using my laws of logs. And so this would be the same thing, 1 plus root 2 all squared. Which is a half of, again, the exponential and the log cancel each other out, and that's just 1 plus root 2 all squared. And on this side, because we have the negative index here, this is 1 over this. So it's going to be plus 1 over 1 plus root 2 all squared. Now this doesn't look too pleasant at the minute, but if we take this second equation and we multiply, the second fraction, and we rationalize the denominator of that fraction, so I'm going to multiply through by 1 minus root 2 over 1 minus root 2, and we're going to square both of those. So when we multiply 1 plus root 2 by 1 minus root 2, what we end up getting, so this is 1 plus root 2 all squared. What we end up getting is a difference of 2 squares, so it's 1 minus 2, which is minus 1. And because we have a square in both of that, we're doing that twice, we'll end up with minus 1 times minus 1, which is just 1. And on the top, 1 times 1 minus root 2 all squared is just 1 minus root 2. If you're not sure of that, take that to one side and just double check it yourself. So that ends up being as a half of, when I multiply this out, I get 1 plus 2 root 2 plus 2. And when I multiply this second bracket, I get 1 minus 2 root 2 plus 2. So this is a half upon, well, again, works out nicely. The 2 root 2 and the minus 2 root 2 cancel out, and we get a half upon 6, which is 3. Of course, if you want, you can use a calculator for these, or if you're asked some simple questions like what's this sine of 2. On the older, slightly older calculators, we have a button especially for that. It's the HYP button. And when you press that button, you'll see that all your options, sine, cos, tan, and you actually get inverse sine, cos, and tan here as well. But then you could press button 1 and it would become sine, and then you would put 2 equals and get the sine of 2. On the other hand, if you have one of the slightly newer ones, it's a slightly different one. You'll notice it doesn't have an HYP button, but if you press the option button and then these options come up and you're looking for option 1. And again, whenever you do that, you see that these same hyperbolic options come up. So sine, cos, tan, and the inverses as well. Again, just a little more similar kind of notes here. This is just handwritten ones, but of sine x and cos x, just written in their exponential form. But just worth noting, I said that the graphs of cos x was an even function. And that's because when you put minus x into this, that's a half e to the minus x plus e to the minus x, which is e to the x. Well, that's exactly the same as what you have above there. So f of minus x equals f of x, and so it's an even function. And likewise, sine, when you put minus x into this, it's a half e to the minus x minus e to the minus x. So e to the minus x minus e to the x, which is, you can take out a factor of minus 1, so it's a minus a half upon e to the x minus e to the minus x. And that's then of the form where f of x minus x is minus f of x, and that makes it an odd function, as we've seen. So again, just in these notes, here's the graphs of sine, cos, and tan. I just wanted to finish this wee section by a couple of wee observations. If you add together cos squared x, subtract sine squared x, then using our exponential functions, that's a half e to the x plus e to the minus x all squared minus a half e to the x minus e to the minus x all squared. And if you take out the half squared is a quarter, square out this bracket, get that, square out that bracket, you get e to the 2x minus 2 plus e to the minus 2x, and then we're subtracting all of it. And actually what you get is a quarter upon 4. All the e to the 2x cancels with minus e to the 2x, e to the minus 2x cancels with e to the minus 2x, and you're just left with the 2 plus 2, which is 4. And a quarter of 4 is 1. And this ends up being cos squared x minus sine squared x equals 1. That is always true. It's almost like a trig identity, but a hyperbolic function identity. That is always the case. Cos squared x minus sine squared x equals 1. And it's a wee bit like we have a trig identity that sort of almost lines up with it. Remember, we have cos squared x plus sine squared x equals 1. Now the second one you could also show and maybe take this to one side and prove it to yourself. Cos squared x plus sine squared x. And when you work through that, you find that's equal to cos 2x. Now again, if we had the trigonometric equivalent, it would be cos squared x minus sine squared x is cos 2x. You might notice here that the link between the two, that the cos in the sine and any number, cos squared, sine squared, and cos 2x is almost identical to the trig version, except where you have a sine term that is multiplied by another sine term. So sine squared x is sine x times sine x. That's a sine squared sine term times a sine term. Sine squared x is a sine term times a sine term. When you have one of those in the trigonometric equation, then to adapt it to get a hyperbolic equivalent, where there is a product of sines, you change the sign. So sine x times sine x if I want I'm going to change the sign to make a hyperbolic equivalent. So this, instead of cos squared x plus sine squared x, actually becomes cos squared x minus sine squared x. Over here, look, I have a product of sines. So if I want my hyperbolic equivalent, this minus sign will change to a plus. So it becomes cos squared x plus sine squared x is equal to cos 2x. And this is called Osborne's rule. Like I say, it's the link between sort of the trig functions and the hyperbolic functions. And we simply change each trig ratio into the corresponding hyperbolic functions. But, and this is very important, if there's a product of two sines, we also change the sign of that term. So for example, cos of x plus y, we know is the cosine x cosine y minus sine x sine y. But look, this is a product of sine terms. So if I want to use Osborne's rule to change to my hyperbolic equivalent, then that sign will change from a negative to a positive. So it becomes cos x plus y equals cos x cos y plus sine x sine y. And again, we're often asked to prove that. As in any proof, work one side until it works equals the other. So I'm going to work the right-hand side here, because I can write all of these in their exponential format. Then multiplying these out, half times a half is a quarter. E to the x times e to the y is e to the x plus y. E to the x times e to the minus y is e to the x minus y, and so on. And when we multiply through, we find that a lot of these terms cancel out. They've got an e to the x minus y and a minus e to the x minus y. They cancel out. An e to the y minus x and a minus e to the y minus x. And so eventually we get a quarter upon 2e to the x plus y plus 2e to the minus x minus y, which is a half upon e to the x plus y. And this factorizes as minus x plus y as your power of e. And that is just the cos of x plus y. And so we've proved that the right-hand side equals the left-hand side. We'll do another one in a wee moment here, but just one more thing to be very careful about when we're doing this, and that is when you have a tan squared term, because that's almost like a disguised form of Osborne's rule, because tan we know is tan squared is sine squared over cos squared. So whenever we have a tan squared term and we want to turn it into a hyperbolic equivalent, tan squared will change sign as well. So tan squared will become minus tan squared. So instead of 1 plus tan squared x, we've got 1 minus tan squared x. Instead of sec squared x, we have a sec squared x. That doesn't change because sec squared x is simply 1 over cos x. There's no signs being multiplied there. So sec x transforms into sec squared x. So the last wee example here, if I know that sine of x plus y is equal to sine x cos y plus cos x sine y, and we've done that since lower sixth maths, compound angles, to get the hyperbolic equivalent, it's going to be the sine of x plus y is equal to, well, this is sine x cos y plus cos x sine y. Now I just need to double check that this sign, neither of these signs change, but look, this is a sine times a cosine term. It's not a sine times a sine. Again, same thing here. I don't have a product of sine terms, and so the signs S-I-G-N-S do not change in front of these. So if I go on then to prove this, let's look at the right-hand side. Sine x is equal to a half of e to the power of x minus e to the minus x. Cos y is a half of e to the power of y plus e to the power of minus y. And again, cos x is e to the power of x plus e to the minus x. And sine y is a half of e to the power of y minus e to the minus y. So if we multiply through this, I get a quarter upon e to the x plus y. E to the x times e to the minus y is e to the x minus y. minus e to the y minus x, and then minus e to the minus x times e to the minus y is minus e to the minus x minus y. As well as that, then on the right hand side here, we've also got a half times a half is a quarter, so I'm going to leave that there, and let's multiply this out. So e to the x times e to the y is e to the x plus y. And again, we're going to get something similar when we do this. We're going to get, minus e to the x minus y plus e to the y minus x and minus e to the minus x minus y. Now see again that some of these things will cancel out. We have a e to the x minus y, and we have a minus e to the x minus y. We also have an e to the y minus x and a minus e to the minus y minus x. So that ends up as we have a e to the x plus y and an e to the x plus y, so that's 2 e to the x plus y. I have a minus e to the minus x minus y, minus e to the minus x minus y, so that's minus 2 e to the minus x minus y. And that factor of 2 cancels with a quarter, and we get a half upon e to the x plus y minus e. And instead of writing minus x minus y, I'm going to write minus x plus y. And that is equal then to the sine of x plus y, which is the left-hand side. And so we've proved that hyperbolic identity.